planning of events that draw large crowds, developing a secure and efficient evacuation strategy stands as a top priority. Protecting the well-being of individuals is especially important in cramped areas, given the increased risk of a panic that can happen. The significance of making decisions regarding the arrangement of a room becomes imperative in the event of a pandemic. In order to expedite the evacuation process, would it be prudent to remove every second row of desks, or would it be more prudent to not simply block them off? FlowCulate proves invaluable in aiding these decisions, providing an effective tool for optimizing spatial arrangements and ensuring a safe and efficient environment. A high room density with all tables results in slower movement. Conversely, increasing the distance between tables speeds up individual mobility. This leads to congestion near the exits. Despite the slower movements in rooms with a high density of tables, the evacuation time will be shorter because there will be less congestion at the exit.
The mathematical modeling used to simulate people flow is based on the assumption that a crowd can be described by a continuum. We make further assumptions such as the higher the density, the slower we walk. We call for conservation of mass in space. Exits are the common destination. How do we run? Firstly, there is a direction we choose, and secondly, we run at a certain speed. The speed at which we walk depends on the density of our immediate surroundings. This dependence is given by a so-called fundamental diagram F, which is derived from empirical data. The direction is determined by the location of the exits, whereby we avoid large gatherings of people, that is, areas of high-density row. We are not looking for the shortest route, but the quickest. The solution of the Eikenall equation puts a cost function phi into the hand whose normalized gradient provides precisely this direction. The velocity field as the driving force of the motion and the conservation of mass lead to the continuity equation, which describes the evolution of the density ρ.
Step 1. Create a site plan for the simulation. This can be a building or another environment. It doesn't matter if it's outside or inside, just one room or several. It just needs enough place for people and a defined exit. Step 2. Fill this environment with elements like start regions, subsections, and objects that affect the simulated pedestrian's path. Step 3. Add further generic details and start the simulation. Once the simulation has been calculated, you can view the results and see where there is room for improvement. This tool will enable anyone responsible for space planning to evaluate existing plans in a simple way and to compare different layout options in order to find the best one. Improving the overall crowd flow management not only reduces the risk of panic, but also ensures that large crowds can move safely through spaces.